PCP stands for probabilistically checkable proofs. It turns out that if you take the verifiers we talked about when we defined the class NP, and 1, you give them access to random bits, and 2, you give them random access into the certificate or proof, then they become extremely efficient in a certain sense. These types of verifiers are called probabilistically checkable proof systems, and the famous PCP theorem relates the set of languages they can verify under certain constraints back to the class NP. In a course on complexity, we would place these proof systems within the larger context of other complexity classes and interactive proof systems. For our purposes, however, we can state the PCP theorem in this way, which is much more accessible.
We'll let capital Phi denote the set of all 3 CNF formulas. Remember, we're assuming that all clauses have exactly 3 literals and that they come from 3 distinct variables. Then a version of the PCP theorem can be stated like this. For any constant alpha greater than 7/8, there's a polytime computable function f such that for every formula phi over a sufficient number of variables, the following 2 things are true. 1, if the formula phi is satisfiable, then f of phi is also satisfiable. And if phi is not satisfiable, then every assignment for f of phi satisfies fewer than an alpha fraction of the clauses. So, if phi is satisfiable, there's a way to satisfy all the clauses of f of phi. If phi is unsatisfiable, however, then you can't even get close to satisfying all the clauses of f of phi. We've introduced a kind of gap here, and this gap is extremely useful for proving the hardness of approximation. Many hardness of approximation results follow from this theorem. The most straightforward of them, however, is that you can't do better than the 7/8 algorithm for max set that we just went over. Not unless p is equal to np anyway. Why? Well, suppose that I wanted to test whether strings were in some language where the language is in NP. And at my disposal, I had a polytime alpha approximation for 3-set, where alpha is strictly greater than 7/8. Then I could use the Cook-Levin reduction to transform my string into an instance of sat that will be satisfiable if and only if x is in L. Then I can use the function f from the PCP theorem to transform this into another set of 3-sat clauses where either all the clauses are satisfiable or fewer than an alpha fraction of them are, depending on whether phi was satisfiable. That way, I just run the alpha approximation on f of phi and see if the fraction of clauses satisfied is greater than alpha or not. If it is, then from the PCP theorem, I can reason that phi must have been satisfiable, and so from the Cook-Levin reduction, x must have been in L. On the other hand, if the fraction of clauses satisfied is less than alpha, then f of phi cannot have been satisfiable, so phi must not have been satisfiable either, so from the Cook-Levin theorem, x must not be in L. Using this reasoning, we just found a way to decide an arbitrary language in NP in polynomial time. So if such an alpha approximation exists, then p is equal to np. Since p probably is not equal to np, it seems like such an alpha approximation can't exist. Many hardness of approximation proofs can be done in a similar way. All that's necessary is to stick in another transformation here, transforming the 3-set problem that has this gap into another problem while preserving a gap, and thus showing that certain approximation factors would imply that p is equal to np.